some algorithms that have a second order bound. And so a bit of background, in standard convex optimization, you have some convex objective. And at each round, you make some prediction, you observe the gradient at the prediction point, and you update your prediction. And as you do that, you get closer and closer to the minimum. In online convex optimization, you are given different objectives at each round. These objectives are convex, and your predictions are allowed to depend on the past or the gradient of the past objectives. An example is when the objective is equal to some fixed convex function plus some random noise. So this would be the case in stochastic convex optimization, for example. Or when your objective is some loss function that depends on some time varying inputs, xt, yt. So this would be the case, for example, in regression. And the objective, well, the goal is to minimize the regret with respect to any comparator u that you may want to choose. And you want the infimum of the regret to be small. So there are many algorithms that guarantee a sublinear regret with almost no assumptions, except that the objective is convex. So online gradient descent, mirror descent. But sometimes you can also take advantage of some curvature of your objectives. So if your objective is strongly convex, then you can use online gradient descent with some nice tuning of the learning rate to have a logarithmic regret. When the objectives are x-concave, you can use online Newton step, for example, to also get a logarithmic regret. But typically, these regret bounds depend on many parameters. So you have alpha for strong convexity, beta for x-concavity, and you also have this g, which is an assumed upper bound on the gradients, and also the diameter of the set u. So if you don't know alpha, beta, and g in advance, then you don't know how to tune the algorithm, and you can't get logarithmic regret. So the question is there an algorithm that adapts automatically to these parameters? Well, at least for alpha and beta, there is. So the MetaGrad algorithm adapts to those automatically. The regret for the MetaGrad algorithm has a term v, a second order term that is essentially the sum of the squared instantaneous regrets. And the expression of this term v allows you to have logarithmic regrets whenever you have a strong convexity and x-concavity without knowing alpha and beta in advance. MetaGrad also has a square root t regrets in the worst case, up to some log t factors. So the idea behind MetaGrad is that the algorithm keeps track of some slave algorithms that have each different learning rate, eta 1 until eta k. And each of these slave algorithms, they run their own surrogate optimization task in the back. The key here is that the surrogate loss is x-concave. And then they send their outputs to a master, which then aggregates these predictions and outputs his own final prediction. So the MetaGrad limitation is that although it adapts to alpha and beta, it doesn't adapt to the norm of the gradients. And this is not a given. As we've seen in the previous talk, if you want to adapt, for example, to the norm of the comparator and the norm of the gradients, well, you can't do it without this exponential term. Well, in this work, we show that it's possible to have to adapt to G and still have this second order bound that adapts to curvature. And the first step, as I said before, is to use this nice gradient clipping trick. And so we came up with a version of MetaGrad, which we call MetaGrad C, that essentially guarantees a regret of similar form as the original MetaGrad, except that it has this additional log term that depends on an input that you give it. So you give it an input B that is essentially the estimate of the norm of the gradients, or the maximum norm of the gradients, times the diameter of the set. Well, there isn't actually a safe tuning of B, because if you choose it too small, then this log term may explode, and it's not bounded at all. A similar term appeared in previous work by Winter-Berger, where instead of this square root sum of little BTs, he had a running max of the norm of the gradients divided by an input B. And so to avoid this log term, we essentially implement a new restart trick that is very different from the standard doubling trick that you may know of. And essentially, you compute the running, you compute the norm of the gradients as you go, and then you trigger a restart whenever this norm of gradients get too large. So to get a sense of how this works, so consider you have these blocks where the algorithm restarts. So here I highlighted the last 2 epochs. And let's give a name to the regrets of these different sections. So it turns out that the restart condition guarantees that the regret before the last 2 epochs is tiny. Well, it's a lower order term, where here BT is just the maximum norm of gradient times the diameter of the set. And it also turns out that the restart conditions ensure that the regret for the last 2 epochs is the same as MetaGrad, without the log-log term that was problematic. And now if you sum them up, then you recover almost the same regret bound as the original MetaGrad, with only small constant factor difference. So this is nice because this bound is homogeneous, and this is a property that usually sought after. The other contribution that we've done is that we improved the efficiency of the constraint optimization. So typically in MetaGrad, all the outputs of the slave algorithm need to be projected on the set U, and they need to be projected on the set U in the Mahalanobis distance. And this can be quite costly because it actually changes in time, this distance. And depending on the set U, if it's complicated, then it can be quite expensive. So what we do, we essentially lie to the algorithm, as Ashok did. And we pretend that the set U is actually a ball that contains the set U. And we just tell the slave algorithm to project on the ball instead of the real set. So we still have to do a Mahalanobis projection onto the ball, but this can be done efficiently. And we only need to project the master on the real set U, but this one is in Euclidean distance instead of the Mahalanobis distance. So it's quite cheap. And finally, MetaGrad requires the horizon T in order to define this grid of slaves. So there are approximately log T slaves. And if you don't know T in advance, then you can't really build up the algorithm from the start. So instead, we define a dynamic grid, and we show that at any given time T, there's at most log T many slaves that are active. And this way, we avoid specifying the horizon upfront. So in summary, we added Lipschitz Adaptivity to MetaGrad. We actually did the same for Squint, which is also another algorithm for prediction with expert advice. So please come to the poster if you'd like more information about that. We added efficient handling of domain constraints. And we also made MetaGrad anytime and also timeless. So if you add any rounds that are just 0, where the gradient is 0, it doesn't affect the bound. That's it. Thank you. Well, if you do a projection on the ball, you usually need to do an SVD decomposition. But if you keep track of the eigen system, you can do the update of the eigen system in D square, where D is just a dimension. So at the end, you can do it efficiently if you keep track of this eigen system as you go.